All right, hello everybody. Yes, welcome to my talk on how you can use GraalVM to run Java-based applications in cloud environments. So for those who haven't heard a lot about GraalVM yet, GraalVM is first and foremost a new way how to run Java, and it has a Java JIT compiler, a so-called just-in-time compiler that is optimizing Java programs faster. When you're compiling your Java programs, you compile them to Java bytecodes, and then the virtual machine later compiles them to machine code. And we have a GraalVM JIT compiler that does this compilation a little bit more efficiently, specifically for very modern workloads. Now, GraalVM has a second application, which is around multi-language support, also for the JVM, because GraalVM itself, as a research project, always had the goal to not just have one language that it supports, but many languages. And so GraalVM can support to run JavaScript, Python, of course, all of the JVM languages like Scala, Kotlin. We also have a WebAssembly execution. We have an R execution, a Ruby execution, and so on. So GraalVM itself understands itself really as a multilingual platform. And then the third aspect of GraalVM is its ability to create ahead-of-time compiled code from Java applications. And in this presentation here today, I'd like to really focus on this third aspect. There's other things out there about GraalVM as a JIT or GraalVM as polyglot, but here I'd like to talk about GraalVM as an ahead-of-time compiler for JVM-based languages. And the reason why we think this is very relevant is that specifically in a cloud environment, this ahead-of-time compilation has many advantages. So if you run an application on GraalVM in a JIT mode, you will take your Java, Scala, Groovy, Kotlin program, and you will type Java my main class, and you will run your application. If you, on the other hand, want to have GraalVM be executed in an ahead-of-time compile mode, there is a two-step process. You first create a native image out of your application by saying native image my main class, and in a second step, you get an executable now that you can just run on its own. This executable does no longer need a Java runtime because all of the code to execute your program is embedded in that executable, and all of the resources are embedded there as well. Now, why would you care about that? Why would you even consider running your Java application like this? And the reason for this is that in a cloud environment, there are certain properties you might care about when running your Java app. First of all, sometimes in the cloud, startup is very important. The specific domain where this is relevant is for serverless, meaning cloud functions, Azure functions, AWS Lambda, Oracle functions. Those platforms often have very short-running programs, and you will actually pay for how long the program runs. So if the program takes like half a second to start up all the time, you have always the overhead costs. So starting fast in a cloud environment can be very relevant. Second, you want to lower your resource consumption. And the reason is that specifically in a cloud environment, the resource consumption is very elastic. Meaning if you use an instance that needs only half the memory, typically you pay half the price, or even less. So using less resources becomes very relevant because it has direct effect on your cloud bill. Security is also very relevant in the cloud, and ahead-of-time compilation has certain advantages, which I will later explain. And finally, you want a compact packaging of your application such that the application can be easily moved between servers or can be easily deployed without the need to, for example, deploy an extra runtime or have very large files that are necessary for deployment. So on these four areas, let's focus on the first one, start fast. And let's compare here the JIT, the just-in-time mode of running an application like Java, with the AOT, the ahead-of-time compiled mode of running an application. So in the just-in-time compile mode, what happens when a Java program is starting? Of course, first, there are jar files and class files that are loaded from disk. They are uncompressed, typically, first, because it's a zipped file. A jar file is a zip file. Then the class definitions are verified. So the Java verifier is making sure that it's actually a valid Java file and doesn't have type errors in there or other things that are outside of the Java specification. And then, finally, the execution starts. But the execution starts first in the interpreter. And the interpreter for Java is typically executing 20 times slower than in the compiled mode. You can test this actually on your application if you want. You can run java -xint to run all your application in the interpreter. And this should give you about a 20x slowdown compared to the compiled version of running the program. So initially, your program will run 20 times slower. And during this slower run, it will also gather profiling feedback. So it will try to understand how the program behaves. It will try to understand what types are involved, how often a certain loop is executed, and it will make note of this information about the program's behavior to then later feed this profiling feedback to the JIT compiler. And the JIT compiler finally grades then of the hot parts of your application, meaning the parts that are executed very often. For those parts, the JIT compiler then grades efficient machine code, and then finally, you can execute your application at peak performance. So there is a lot of steps involved here. And if you compare this with the ahead-of-time compile mode of running your Java application with a native image, there you basically load the executable from disk, and you're done. You execute at peak performance because the application is already fully converted into machine code. So it doesn't take a lot of insight here to understand that, well, on the ahead-of-time compile mode, the startup is a lot better. And a lot means actually an order of magnitude. So, well, it's a nice theory. How does it work? There is, for example, an example here from a Micronaut web server that's written in Java that can start up in 6 milliseconds. So this is previously unheard of a Java application, a Java web server that would often they start at least a couple hundred milliseconds, they need a startup. Here we can start a full web server in 6 milliseconds. So the startup benefits of ahead-of-time compilation are really dramatic. Typically, it's about 2 orders of magnitude. So at least somewhere between 1 and 2 orders of magnitude, somewhere between 10 and 100x faster in startup. So startup is nice, but it's not always the most important thing. Sometimes you not just want startup, but you actually want to run your application for a long time, but you still want to minimize resource consumption. You still want to use less resources for your application. And here we can think about what are the memory requirements of the application. In the cloud, typically you pay for memory. If you look at the pricing of typical cloud providers, it's often the case that it's priced based on the memory consumption of the instances that you book. So in the JIT mode, what type of memory is occupied by Java application? So first of all, there is a garbage collector and a runtime component of the VM that needs to be somewhere loaded in memory. OK, that seems clear. But then there is other parts that are necessary that are to be loaded in memory that are not directly associated with your application. So for example, there is metaspace class files. In the hotspot Java virtual machine, you can specify max metaspace or initial metaspace size because all the class file definitions, including all the names of the methods and local variables and classes in there, need to be loaded and put into the metaspace. All of this occupies memory. Then the profiling feedback also occupies memory because the interpreter, when it gathers information about what types are used in the application, also has to store it in memory. And it occupies memory on the machine that Java program is running. The compiler needs memory when it does the actual compilation. These memory requirements can be quite high. The good thing about those memory requirements are that typically, if you run in JIT compilation mode, after some time, your application should reach a stable state, where initially you have a lot of compilations, but later on the compilations should die down. So the compilation data structures lead to a peak memory usage during the startup of your application. This should later on not play a big role. But what still plays a big role also later on is the dynamic code cache, because the dynamically compiled machine code also needs to store it somewhere. And this storage is the code cache. This is why on a Java JIT compilation mode, when you run Java, you specify typically also a max code cache size, because you need to specify how much memory is reserved for the JIT compiled machine code. And after all of this, finally, yes, there's also some memory that the application actually uses for itself. But it's important to note here that in addition to the application payload, there's a lot of other data structures in memory that are not related to how much memory your application actually uses. They are more related to actually how complex your application is. Meaning if your application has a lot of code involved, so there's a lot of, the jar files are very large, the dependencies are very deep, then this additional memory cost is higher. Now, in ahead-of-time compile mode, there is still a garbage collector that is part of the ahead-of-time compiled image, so that machine code has still to be loaded from disk. And then there is also now a new component, which is not there in JIT mode, which is the application's machine code that needs to be loaded from disk. And there is not anything more, meaning then it's just the application payload. So compared to the JIT mode of running your application, you save very substantial amounts of memory. You save the dynamic code cache, the metaspace class files, the profiling feedback, and the compilation data structures. And how big these savings are for your application, of course, depends on how is the relation of your application between the application payload size, meaning how much memory does your application need, versus how much code is loaded. The less memory your application needs, the higher are the potential savings in memory from using ahead-of-time compilation here. And to illustrate it a little bit, I have here measured the CPU and memory usage of a little web service. And on the left, I have measured it in the JIT mode, on the right, on the ahead-of-time compile mode. In red, you see the CPU usage of the machine that this is running on. And what you can see is that at the beginning of the application, in the first few seconds here during startup, the application actually saturates the CPU quite a lot. And this is because there's many compiler threads running, loading the application and compiling. This has another effect on your machine, which means that if there are other services running on the same machine, they might be affected by this. So it's not only the time to start up, which is much higher in the JIT compilation mode, it's the total CPU cycles that are necessary to start up is even more skewed and is even higher compared to just the clock time. This also means that the weaker the machine is that you provision this with, the more effect this longer startup will have on you. And it's not just during startup. You can see on the left side during JIT mode also, I have here the application and I give it a few requests. And after a certain request, suddenly there is some additional code exercise in the application. And there you then have a spike in CPU usage. So suddenly you use even more CPU because there needs to be more compiled of the application. On the right side, you see the ahead-of-time compiled version of this. And first, during startup, you see almost no CPU consumption. And then you see also no CPU consumption later. Only when there's an actual request sent, there's a very small spike of CPU consumption. So the total CPU consumption on the right, which is shown in red, is much lower than the one in left. And it's not just CPU consumption here. I'm also measuring the memory of the application that is used, the resident set size. And the scales are a little bit different here, because on the left side, you can see the real memory go up to 150 megabyte, whereas on the right side, the real memory has only 30 megabyte. So for an application that itself doesn't use much memory on its own, the savings in memory can be super substantial. In this case, it's a 5 times saving in memory. And it's not just the saving per application that is great, but there's also better memory scalability in case you start multiple instances of your application. So if on the same machine I'm running multiple instances of the same application in order to scale up and down during a peak, I would like to scale up, for example, run a few more processes. Now on the left side in JIT mode, all of the part on the bottom is duplicated. So you will have now per process, despite the fact that it's running the same program, you will have a new dynamic code cache. You will have a new metaspace class files. You will have new profiling feedback, and you have new compilation processes that are running. Whereas on the ahead of time compiled part, if you run multiple of these images on the same machine, only the application payload is what you pay. So specifically for scaling up on a certain machine, this has big advantages. And we have here a little measurement from, we're using here Quarkus Apache TCAR benchmark, where we are running this program. And on the very left, we run the program just 1 process. And then we run the program 2 processes, 3 processes, 4 processes. And the amount of memory necessary in the JIT mode, here on hotspot C2 measured, is going up quite a lot, whereas in the ahead of time compile mode, you keep relatively flat because the additional memory you pay is much lower. So now we had starting up fast, low resource usage. We also want to be as secure as possible. So how does ahead of time compilation help security? And so the answer to that is that it reduces the possible attack surface. So first, in our ahead of time compilation mode, there cannot be new code loaded at runtime. So there can nobody inject new code into the system because all of the code needs to be available at build time. Second, only the path through the application that is reachable or proven to be reachable at build time is actually even included in the image. So if you have some unknown dependency that you actually not use, it will not even end up in the native image and can therefore not be later exploited. Because there could be an exploit on a library that you actually have never heard about, that you would ever use it, but suddenly it becomes reachable dynamically in JIT mode, but in ahead of time compile node, it might not even be in that image. Then, in our ahead of time compile node, reflection is disabled by default, and it needs an explicit include list. So a certain reflection path that an attacker might be able to use could be prohibited because only the reflection paths that you specify are allowed in the ahead of time compiled image. Deserialization is the same thing. Sometimes there can be an attack on a Java program by deserializing a class that the Java program wasn't aware of. In the case of our ahead of time compilation, deserialization also needs an include list, meaning only classes that were specified to be deserialized are allowed to be deserialized. And finally, the just-in-time compiler itself is a very complex piece of software. So possible attacks could be to trigger wrong compilations, to trigger a crash on that compiler, or to have an attack using JIT spraying, where you would try to get this compiler compile a certain pattern many times to create a machine code gadget that you need for attacking the program. And this kind of JIT spraying attack in ahead of time compiled mode is also not possible because there is no JIT compiler in that program. So to summarize, in terms of security, we are reducing the attack surface. So we make less things possible that were possible before, and we are therefore less attackable. Finally, on the packaging question, like what about compact packaging? For ahead-of-time compiled mode, you have a single executable native image. And this means in this image, all of the relevant code is already included. So the GVM runtime and JDK library code is all included. You do not need to distribute a separate Java runtime. It is the application itself that contains everything. This application, you can, by the way, use even a static linking of C libraries and then put into an absolute minimum Docker container. So if you want the possible minimum Docker container, use static linking of the image and then put it into a from scratch Docker container. Unreachable paths are excluded from the application before it is deployed. This can be an advantage specifically if you have large library dependencies where in reality you only use a small portion of that library. Because all of the code that is not reachable, that is not seen to be reachable from your application, is discarded before this image is built. There is a disadvantage here in that the Java runtime cannot be shared because every image has its own runtime. On the other hand, it's also a possible advantage because it means that your applications can be patched individually. So you can run applications with different Java versions, different minor versions of Java, all side by side because each application has the runtime included in that package. And how big is such a package? And for this, I have here an example. I have a small command line utility in Java. I've written this one, and it is just listing directories. So it's the equivalent of the ls command in Linux. It's listing directories. And if I want to deploy this to my users, the smallest Java runtime that I can do is about 39 megabytes. And yeah, for a command line utility, that's relatively big. And it's one of the reasons why Java is currently not very popular to create command line utilities with. Now, I can actually compress this GRE, so I can zip it up, and I can get smaller. I can get you to about 14 megabytes. If out of this small program I create a native image, the native image is only 5 megabytes. So it's already much smaller than the smallest compressed GRE, because it only includes from the Java libraries the parts that it needs, meaning access to the file system and directory listings, and not other parts that it would never reach. And finally, this image, of course, can also be compressed. It can be compressed with an executable compressor, for example, UPX. And this compression gives another about 3x, meaning the final executable here that is running this list directory utility is only 1.8 megabytes in size. And it's still relatively big if you compare it with, let's say, a C executable, but it's already an order of magnitude smaller than what you can reach currently with other means for Java. And we are continuously, as the GraalVM team, working to get this down to the level of C, which is our ultimate goal. So these are the 4 advantages that there are when you run here a Java application with GraalVM native image. It starts 1 or 2 orders of magnitude faster. It has lower resource consumption, lower memory consumption. You minimize vulnerabilities of your application, and you have a more compact packaging possibility. Now, this sounds all great, so what's the catch? Like, what's the problem with it, or what are the downsides or disadvantages of this? So one disadvantage is that you need reachability metadata to assist our static analysis to create this compact image. And for this, for example, certain Java programs rely on certain features that we have to disable. We disable them to get a more compact image. We disable them sometimes also because it helps, to a certain extent, also security. So there is no unknown class loading allowed, and also no unknown reflection. And therefore, we typically recommend, when you use native image, that you use an existing framework that has support for native image. Because those Java frameworks have done already a lot of work to make sure that the GraalVM native image compiler gets the correct information. And so therefore, when you use native image, it can be very hard to use on an older large code base. It can be, however, quite easy if you start a new application to develop it for native image by using one of these 4 frameworks. And those 4 frameworks are, one of them is Micronaut, Micronaut.io. We are, like the GraalVM team and the Micronaut team, we're very close together. We have Helidon.io, which is another framework for web development that uses native image. We have, of course, Quarkus.io, which is the solution from Red Hat that is based on native image. And there is also a very strong effort going on from the Spring team at VMware to create experimental support for Spring applications to be compiled with native image. It's called Spring Graal Native. You can see here the place where they have various Spring projects that are then compiled to native image. And we have an ongoing, really great collaboration with the Spring team to make native image work for all Spring applications. So the other downside is there is a build time step required. So this means in your CI/CD pipeline, as you deploy your application, you need a certain amount of computational effort because you need to do the ahead-of-time compilation. This is something that typically will be hidden while your program is running in JIT mode, but here it is necessary to do ahead of time. For this, it needs a powerful machine, and it needs to know the target architecture and operating system where you will deploy the application. You can use for this, by the way, also GitHub Actions. So that's specifically interesting if you want a command line utility for many different platforms. You can configure GitHub Actions to create these native images for you. We have on the GitHub Marketplace a plugin for GraalVM on GitHub Actions. And the idea here is that you develop your application in JIT mode because you want to be fast during development, and then only at the final step when you deploy your application, you go to ahead-of-time compile mode for that final deployment. And one disadvantage is also that for profile-guided optimizations, typically they would happen at runtime as the JIT compiler profiles the application. If you want the same peak performance, including profile-guided optimizations, you need to gather profiles at build time. The way this works is that you run a native image and run it to create it with an instrument, and then run an example workload. And from that example workload, you get the profiling information, profile.iprof. And with this profiling information, you can then create an optimized native image. So this requires also one more step at build time of something that would otherwise happen automatically at runtime. Now, the advantage of this is that you can actually choose the workloads that your application wants to optimize for. Because the workloads that you choose during gathering these profiles will influence the compiler to make the decisions to optimize for exactly this kind of use cases. So GraalVM is an open source project. We're on GitHub. We have many contributors, and we are, of course, one of the largest Java open source projects because GraalVM itself, including the JIT compiler and VM, is almost entirely written in Java. The GraalVM team is maintaining about 4 million lines of open source code on GitHub with GraalVM and the related projects. So this is the GraalVM team at Oracle is maintaining these amounts of open source. You're welcome to join the community, look at our Slack channel, look at our GitHub projects, and yeah, also report bugs there on GitHub. We hope to be very responsive to anybody who is giving us feedback there. You can also just download GraalVM and get started with it. Go to our website, graalvm.org. You can have 2 editions of GraalVM. There's the community edition, which is an open source build, and that's community supported. And we have an enterprise edition with commercial support from Oracle. And the enterprise edition is, by the way, free to use on the Oracle Cloud. So if you want to get started as well, go to our cloud. GraalVM Enterprise is included in whenever you use Oracle Cloud, even if you use only the free tier of the Oracle Cloud. With that, I would like to thank for your attention. There will be no questions on the keynote, but I will be at the Oracle booth. So if you want to have some more questions, I will be hanging out during the next few hours and try to answer anybody's question who wants to. You can also join us and get this awesome Oracle T-shirt. It's a modest version. You know, it doesn't say Oracle very big on it, but it's an Oracle T-shirt here. You're welcome to join us at the booth, fill out a developer survey, and get a T-shirt and get to ask questions. Thank you very much for your attention. I hope you could get something over here and enjoyed it. Thank you very much.